In the early 1950s, engineers had a problem. Well, they had many problems, but the one we're going to talk about is the booming television industry that in the half-decade since the Second World War had sold probably around 6 million black and white TV sets to US consumers. And of course, what's better than black and white? Well, color. And of course, consumers were already seeing color in things like color photography and movies, and it was really clear that color was going to be the next best thing for television. But with 6 million television sets out there, well, you had to keep those 6 million consumers who had paid a couple of $100 per television set, and that's a couple of $1,000 in today's dollars. Well, they had to remain happy, because if you told them suddenly their old black and white TVs wouldn't be compatible with the new color TV signals, and they'd have to buy an even more expensive set, well, that would be a lot of angry people. So the requirement for color TV was that it had to be fully compatible with the signals for black and white television. And in the old days, in the 1950s, all of that was, of course, analog electronics, and that made it a real challenge. The good news was that even in the 1950s, we had a pretty good understanding how one might create a color television system, and that was from all the work that had been done for color photography and movies. We knew that you could take a red and a green and a blue image, and if you mixed them together properly, you could trick the eye into seeing color, and it was very good color. That's what you're watching right now. And, well, that seems simple enough. All we need to do is take 3 television channels and use them for each of those images, and we have color TV. But the problem with all of that is, well, we don't have that many channels available, certainly not in the 1950s. In fact, most television sets only had about 12 channels available, depending a little bit on where you were. And worse than that, you could only really use about 6 of them to prevent interference from adjacent channels, perhaps in different regions. So that really meant that you only really had about 6 channels available in any given TV market. And now, if you needed 3 of them for each color TV station, it really meant that you only had enough channels for 2 channels in any particular market. And of course, that would upset many people who already could see 3 channels in some of the larger markets. And it would really upset the TV station owners, where one of them would probably have to shut down. So that was not practical. So what we needed to do is find a way of crunching down those red, green, and blue channels and put them together in such a way that they could sit on top of a black and white television channel, and do it in such a way that the black and white TV sets could still receive that signal. And of course, in those days, we didn't have fancy digital electronics, which makes that fairly simple. What we had to do is do that entirely with relatively crude analog electronics. And when you think about the fact that instead of transistors those days, you just had electron tubes, well, the electron tubes were the size of light bulbs, and you couldn't use that many of them either. So it was a real engineering dilemma. At this point, you might be saying to yourself, well, isn't there a simpler solution? Couldn't we just add more TV channels? In fact, we know that at the peak of analog television, there were 83 TV channels. Well, the problem in the 50s was the VHF channels, 2 through 13, were between 30 and 300 megahertz, and those frequencies were quite doable with the tube electronics that existed at the time. The UHF channels that we used later on were up into the UHF band between, well, 300 megahertz, and I think they went up to somewhere around 800 megahertz, which was at the very limit of tube technology. In fact, there were some specialized tubes developed just before World War II called acorn tubes, for instance, that were made tiny so that the electrons could move across the tube really quickly and do frequencies just barely reaching into that range, but it was by no means an everyday technology and not something you wanted to mass produce and put in the homes. So those extra channels were really unfeasible. The other question you might have as well, we certainly had hundreds of AM radio channels, for instance. Why on earth can't we do that with television? Well, an AM radio channel was somewhere around 10 kilohertz wide. And just to put things in perspective, the human ear can generally hear up to 20 kilohertz when you're young, maybe down to 10 kilohertz when you're old. And a 10 kilohertz channel, for technical reasons, can only really give you about 5 kilohertz worth of audio, which turns out to be good enough. Well, that's relatively small. A TV channel is generally between 5 and 10 megahertz wide. It's so wide that at that sort of range, it is 4 or 5 times the bandwidth of the entire AM radio band. Well, it's because of the amount of information that has to be sent. And the way a TV system works, certainly the old analog ones, is you scanned the screen from left to right with an electron beam. And when you came across something like my face here, and well, scanned from here in the dark area, came across my face, which is relatively bright, the voltage would suddenly shoot up. And then as it crossed my face and then got into my rather dark hair, the voltage would drop quickly. And that very quick rise and fall of the electrical voltage that's generated and transmitted corresponds to high frequencies. And it turns out with the number of scan lines you have to create and the speed you have to do that to get a nice stable TV image, which was basically in those days 500 lines from top to bottom and probably effectively 500, 600, 700 lines across, depending on how good your electronics were, well, it computes to needing those super high bandwidths. So that's why you couldn't just add them in the VHF band, which was also being shared by a whole bunch of other things. So that really set the stage for having to compress the black and white signal and color signal together to fit the existing channels. So how did we do it? Well, the trick was to take a high frequency sine wave and add it to the black and white video signal. And that frequency was 3.58 megahertz, at least for North America. And you say, what would happen if we did that? Well, you would get a whole bunch of vertical lines across the black and white signal. However, being very high frequency, they were very close together. And I'll try and show you that on the screen using a much lower frequency, because if I try and use high frequencies like that, well, you may not actually be able to see them depending on the nature of the screen you're looking at. Anyway, that would still be quite annoying, even though you could sort of see the black and white image through that screen, I'm going to call it. But here's the trick. What they actually did was shifted the 3.58 megahertz frequency just a bit so that the peaks of those lines on one horizontal scan line would line up with the valleys of those lines on the following horizontal scan line. So what you'd get is the peaks and the valleys, the brighter and the darker points, always being next to each other. Now, in the really old TVs, the original ones from the late 40s and early 50s, well, most of them didn't even go up to 3.58 megahertz in terms of video anyway, and that signal did not get through at all. If it did get through, well, it would look something like this. And, well, you can see there is a somewhat annoying dot pattern, but in reality, that pattern is only there where there are bright colors, and it turns out in most cases it's not really a problem. Okay, that's all good and well, but I still haven't told you how we get color on it. Well, so here's the trick. You've probably seen a color diagram like this, and the colors form a circle. And essentially what that circle does is shows all the different color combinations you can get from mixing together three primary colors. And you'll notice they sort of form a circle around white in the middle. And going out from the middle, well, you get more and more intense colors. In other words, going from the center to, say, red, you can start off with white, get some sort of a pink, get more of a reddish color, and then eventually end up with a very intense red, the primary color red. And indeed, you can do that for every other color combination that's available on the screen. And since it's a circle going around that center white area, the easiest thing we can do to specify a color is give it an angle. So starting at 0 degrees, we can work our way around the circle, and every color is assigned an angle. And the really neat thing about a sine wave is, well, the shift in a sine wave from, say, its starting position over, in other words, delaying the sine wave by a greater and greater part of one of its cycles, is generally also specified in the form of an angle. So what we can simply do is say the color on any point of the screen is going to be the position of the peaks of that sine wave in degrees. And by just shifting the peaks of the sine wave just slightly anywhere on the screen, well, we can generate all of the colors that are available from a mixture of 3 primary colors. And it turns out that was fairly easy to do with analog electronics. And it's really because a lot of the color work can be done by adding and subtracting things. Red plus green plus blue equals white. Well, those types of calculations are fairly easy to do just by adding signals together in an analog amplifier. Well, that's very nice, but we have one other problem. We don't just want the color, we do want that intensity, how far away the color is from a colorless white to a very intense primary color or a very intense mixture of a couple of primary colors. Well, that was also very simple because all you had to do was make the amplitude, the height of that sine wave that we've added to the video signal, correspond to how far away from white the color is. So if you had a white, you ended up with absolutely no carrier. You wouldn't see dots on the screen at all. And if you did have a slightly pinkish red, you would have the correct angle for that color, and you would increase the amplitude of the dot pattern just slightly, and that would indicate it's a pink. And if you wanted red, well, you would crank up the color, well, much like here, and see a really intense dot pattern. And that would be how you convey all of the colors. This is the standard bars test pattern for NTSC, and sure enough, if we look at the black and white version, we have a whole bunch of dots on the black and white picture, but the black and white picture is very visible. But at the same time, on a nice color set, well, the colors are beautiful. All right, problem solved. We have a compatible color television system. Well, not so fast, because here's the problem. When we modulate our color images, our color information onto that 3.58 megahertz carrier, it turns out it starts spreading out from 3.58 megahertz. In fact, if we were to take our, say, 4 megahertz bandwidth black and white signal and now take the color parts and modulate it that way onto 3.58 megahertz, well, they'll start spreading out all the way down to 0 megahertz, because it'll try and spread out in 4 megahertz or so in either direction from the carrier. And that's going to, of course, look bad on a black and white signal. It's also going to make it very hard to separate the color from the black and white in our television set. All right, so what can we do? Well, it turns out there's actually a very good and very useful aspect of human vision that we're going to use. And what it is that we can see detail in black and white way better than we can see it in color. And that's all has to do with how the rods and cones are set up in the eye and how the visual system processes the data. The bottom line is the detail we see in color is not nearly what we see in black and white. So what can we do? We can take the information we've used, the red, green, and blue images if you want, to modulate that 3.58 megahertz sine wave and reduce their bandwidth down to essentially make the image a lot more blurry in a color sense in the left-right direction on the video screen, because we can't see it anyway. And it turns out we can do that quite considerably. It also turns out that some of the colors we can see in more detail than others. Without going into all the nitty-gritty of that, the bottom line is we're able to reduce the bandwidth of the color signal to a half or maybe a third of the bandwidth of a black and white signal. Okay, we've made the color a little bit blurry, but we can't see it. We now have all the color information up in the higher frequency range without any of it getting into the lower frequency range of the black and white signal at all. And that's great. And problem solved. Once again, not so fast, because here's the problem. In the color TV set that we're going to charge consumers an absolute fortune for, and they expect to work properly, well, we're going to have a nice sharp black and white signal. We're going to add the color information to it, and what happens? Well, the nice sharp black and white signal, if we had something like a house, the scan line across the screen going from left to right, well, over here when we get to our house, which is bright whitewashed, the electrical signal goes straight up to reflect the higher amount of illumination, and then, well, it stays high, and then we get to the other side of the house and maybe we have a dark hedge in the background or something, and the signal drops. Nice crisp edges to the house. Well, what about the color information? Well, we've dropped its bandwidth, meaning we've cut out the high frequencies, and the result of that is it takes considerably longer for the electrical signal we're receiving to rise to the peak it has to be, and then it also takes considerably longer for it to drop back to a dark background. And what happens if we now mix those things together in our color circuitry? Effectively, we're superimposing them on top of each other. And what does it look like? It looks like the slightly blurry shape of the house has been shifted a bit. The color doesn't quite line up now with the very sharp black and white signal. And if you've paid maybe $500 or $1,000 for a color television set in the late 1950s, so that's probably closing in on $10,000 today, you'll be really upset if the color part of the image doesn't seem to quite line up with the black and white part of the image. So what can we do? And that is the subject of today's video. That's what I've been really working up to. What we have to do is we have to somehow delay the black and white signal so that it lines up just a little bit better with the color part of the image that we've reconstructed through all that rigmarole with the 3.58 megahertz carrier and reducing the bandwidth to make it all fit in the black and white signal. So how do we delay the black and white signal to make it line up with the color images? Well, today it'd be real simple. We take a few million transistors on an integrated circuit and it's all done. We didn't have that luxury back then. Well, the first way is pretty obvious and would have been pretty obvious to engineers back then. And that is you take a big spool of cable like this, and this is just regular TV cable. What you do is you feed the signal into one end of the cable and you get the signal out the other end of the cable, and because the signal travels through this cable at what effectively is the speed of light in the cable, there is a certain delay. Well, the speed of light is about 1 foot per nanosecond, and I know that's going to upset a lot of metric people, but In the case of the speed of light, it's way more understandable to, well, you know how big your foot is, and a nanosecond is some incredibly short period of time, 1/1000th of a second, which means nothing to us, but at least it gives us some sense of how far light might go in a pretty short period of time. Well, the speed of light in a cable, because of the insulation in the cable and also because of the geometry of the two wires in the cable, in this cable it's a outer shield and an inner wire, you end up with a certain amount of inductance and capacitance per unit length, per meter in most modern calculations. And it turns out the speed of light in a cable is essentially 1 over the square root of the inductance times the capacitance per meter. And what does that mean in real terms? Well, it really means the speed of light in this cable is probably around 60, 70, or 80% of the speed of light in air. So it doesn't go quite as fast as 1 foot per nanosecond, but some reasonable proportion to that. Now, it also turns out that in most color TVs, the amount of delay we need is somewhere around 250 nanoseconds, 250 billionths of a second, up to 1 microsecond, 1/1,000,000th of a second, depending a little bit on how much we've cut off the bandwidth of the color information. And what that would mean is, well, if this cable operated at the normal speed of light for, say, 500 nanoseconds. A very typical number is you'd need 500 feet of cable because the speed of light is somewhat slower in this cable. Well, what you might only need is 400 or 350 feet or something like that. It still would be a pretty big bundle of cable to include in your TV set, even if those TV sets in those days were really the sizes of pieces of furniture. So that's not very practical, even though it's doable. So what can we do? Well, that's where these magical things come into play. And what they are is they're called delay lines. And what they do is they delay the black and white signal in a color TV, and these things were out of some vintage color TVs. I pulled them out many years ago. And for instance, this one here will delay the signal about a microsecond. This one will delay it about 500 nanoseconds, half a microsecond. And it's certainly a lot smaller than that large spool of cable. So how on earth does this thing slow down the propagation speed of electromagnetic waves going through the device? Effectively, how does it slow down the speed of light? Well, you might remember that I said that the speed of light, the propagation speed in a device like a cable, is something like 1 over the square root of the inductance and capacitance per meter. So what we need to do is effectively increase the inductance and increase the capacitance of the cable. And what they did to make these things is, the first thing is, well, let's take a cable, and what we'll do is we'll take one of the wires and we'll wind it in a spool to make a long coil. And because the magnetic field will be nicely confined within that coil and there'll be a lot more wire, it turns out that greatly increases the inductance per meter. And so we've solved the first part of the problem. We'd also like to increase the capacitance per meter. And the way you increase the capacitance is you increase the surface area between the two conductors in the cable. And what you also may do is try and move those conductors closer together. And the way they did that in these things is, well, just inside this coil, in fact, what this coil is wound on is a strip of foil, essentially like aluminum foil. It's probably copper foil, because that's probably easier to solder to. But just inside this device is a long strip of foil. And what that does is increase the capacitance along the device. The coil increases the inductance along the device, and that really slows things down. And if you figure this thing is about a delay of 1 microsecond, 1,000 nanoseconds, and well, it's a bit over 10 centimeters long, but I'm going to say it's 10 centimeters long to make the calculation easy. Well, what that really means is the propagation speed, the speed of electromagnetic signals, the speed of light in this device is probably somewhere around 1 centimeter per 100 nanoseconds. Well, that is way, way slower than the 1 foot per nanosecond type speeds of light in free space. So these devices are what we actually used in old vintage color TVs to align the black and white signal with the color information that we had so painfully compressed and then extracted. So how can we look at one of these things operating? Well, the first thing is we need a nice clean signal to look at, and what I've done is set up a signal generator to generate something like a 250 nanosecond pulse, a nice rectangular pulse. And what we're going to do is attach that to the 2 inputs of our delay line, and we'll also attach the probes of the first channel of our oscilloscope to that so we can see the signal we're sending into the delay line. And at the other end of the delay line, we're going to attach the scope. But before we do that, we're going to actually add a 1 kilo ohm resistor between the 2 terminals of the line. And the reason is, just like a coaxial cable, this line has a characteristic impedance. And what we need to do is we need to use a similar resistance to the characteristic impedance of the line at the end of the line to prevent reflections coming back and messing up things. So we've attached our 1K resistor here. Now we'll attach a scope, and sure enough, what do we see? We see our significantly smoothed off rectangular pulse appearing at this end of the line about 1 microsecond later, as we would have hoped. Now, why is it smoothed off? It's smoothed off because this device here has a rather limited bandwidth that gets rid of a lot of the really high frequencies. And, well, that's what makes a square wave into a more rounded wave. And just like we talked about going from the high bandwidth black and white signal to a lower bandwidth color signal. But it's certainly more bandwidth than needed to successfully delay without smoothing the black and white signal too much. Okay. Now, you might be saying, but is it really delaying it? Well, what we might want to do is just to confirm that, look at the signal halfway along our delay line, and we should see half the delay. Now, strangely enough, this delay line was actually built by taking 2 copper windings, this one, and joining them together in the middle. I don't know why they did that. I've never seen any other delay line built that way. My guess it's some sort of calibration thing, maybe to add or subtract some windings if it was too slow or too fast. But the nice thing is there is a joint between the 2 copper windings in the middle here that we can attach the scope. And indeed, that's what we're going to do. And well, there you go. If you look at the signal we're getting from the middle of the line, it's delayed by exactly half the amount. Incidentally, it's also considerably higher in amplitude, and that's really because of the losses that are occurring along this line. There's a certain amount of resistance in the copper windings that are very fine wire, and because they're higher frequencies, there's probably a skin depth effect occurring, and who knows what else. There's probably eddy currents occurring in the foil that we have under the winding, but the bottom line is, even though it's attenuating as it moves along the line, we are getting a nicely delayed signal, and that was good enough for old color televisions. And what we really should do is now look at that inside a real color television set. So here's a classic standard 1980s television set. It's all analog, although it's transistorized other than the main picture tube. And, well, if we turn on the volume, that was a very typical sound when you had no channels on. But now if we turn it on to channel 3, there we go, we have a test pattern. So you may wonder, where in the back of this thing is the delay line? I'm going to pull out the circuit board so we can see things a bit better. And, well, the delay line is hidden in this metal can over here. And the nice thing is, behind the can, we have a test point for the video going into the delay line. And one of the resistors around here has the output of the delay line. So what we're going to do is hook up an oscilloscope and see if we can actually see the delay that's taking place. The signal going into the delay line, and looking at color bars here, those very intense colors, you can see the top of the signal is quite a thick band. Well, that's that 3.58 megahertz carrier that we talked about, and it's relatively thick because the amplitude of the carrier is high because those colors are very intense. If we look at the signal on the second scope channel, that's the signal coming out the other end of the delay line. And if we look at the whole line, well, we can't see an effective delay. What we can see is we're not getting much color information at all. It pretty much is all stripped out. I think the delay line has removed some of it just by its natural filtering. What really is important, though, is can we see a delay? Now, a line from left to right, one horizontal scan line, which is what we're looking at, is about 64 microseconds long. And we're talking about delays that are less than a microsecond, and we clearly can't see that. So what I have to do is adjust the sweep speed of the scope to essentially expand the horizontal scale on the scope so that we see time spreading out. And if we look at a good sharp transition point, one of the bumps either in the test pattern staircase or the sync pulse or something like that, we should be able to see a short delay coming from the output of that delay line. And if we do that, well, sure enough, the signal coming out of the end of the delay line is lagging the input signal by about 500 nanoseconds. That's half a microsecond. And that's pretty much exactly what we would expect for a typical color TV set of that era. And it's kind of neat to see it in action because delay lines like this are becoming increasingly rare these days. In fact, you really never see them other than inside of old vintage TV sets like this one. Now, there were other types of delay lines in the days of analog electronics, and I wanted to show you a couple of them. And the first one I want to show you is this one. This is an ultrasonic delay line, and the device that I'm holding is a dropout compensator from an early VCR. What's a dropout compensator, you might ask? Well, in a VCR, the videotape is nowhere near a perfect recording medium, and indeed what you often have happening is bits of video being lost because of imperfections in the tape. And that can be rather disturbing because what you see that is black streaks along your image. Now, the neat feature of video is, in most cases, the color and black and white information of a line above another line is about the same. There's not much difference between two lines in the image that are next to each other. So what the trick was is, if you had a loss of video on one line, you simply took a copy of the video on the previous line, the line above it, and substituted for the missing video information. And how did you do it in those days? Well, what you did is you used a 64 microsecond delay, the time that one scan line took, and you applied that to the video signal. And what that meant is, if you lost video because of a defect in the tape, you could switch to the delayed video signal and hopefully get a perfect piece of video to substitute for the otherwise black streak on your screen. And a delay line was used. Now, this is an ultrasonic delay line. The way it works is you have an ultrasonic transducer, one that can go well up into the megahertz range. And what it does is it sends out an ultrasonic signal which bounces through an intricate pattern through usually some sort of glass or ceramic substrate in here. And at the other end of the device, or the other side of the piece of glass or ceramic, there is another transducer, a receiver that gets that signal. And if you set up things right and you know the speed of ultrasonic sound in the material you're using, you can build the whole thing to produce a 64 microsecond delay. This was also commonly used in European television sets because for both PAL and SECAM, which we haven't been talking about, I've been talking about NTSC, although I didn't mention it. Well, in PAL or SECAM, you actually do need a copy of the previous line to do your video encoding, but that's the story for another video. There's another type of delay line, and that's this. And this was an early computer memory. And the way it works is there is a long spool of metal wire in here, and it's also ultrasonic in the sense that we use it to delay a signal being transmitted through that wire. And what happens in the case of a wire delay line is it's operated by twisting the wire rather than sending a compression type audio signal through it. It turns out that works very effectively for a long bit of wire, and I guess the wire in these lines was often a meter or two long. That's 3 or 6 feet if you're in a non-metric country. And this type of line typically delayed things as long as a millisecond, or more likely probably around half a millisecond. And I think some of them didn't have quite as high a bandwidth as one might expect, probably more in the megahertz type range or half megahertz. And it turns out these things could effectively store what amounted to 500 bits of information, maybe a kilobit of information if you were lucky. And indeed what they were used for is things like memory for early video terminals. And the way it would work is you'd send all your bits in a bit stream into one end of the line, and a millisecond later they'd come out the other end. Now, if you did nothing, you'd lose them. So what typically happened is you attach the output through an amp back to the input, probably with some signal conditioning, and recirculated the data through it. And that worked pretty well for things like video terminal displays. And I would suspect if you're old like me and might have seen some early video displays in airports, which I thought was quite fascinating as a kid because that was probably the first computer display I'd ever seen. Well, they were probably operated using this type of delay line, an early computer memory. So that was really the beginning of digital, still using analog technology. Now, there actually is a modern application for delay lines. And, well, this is a computer motherboard, a fairly old one, but it'll do. And if we look at it very closely, maybe with a magnifying glass, what we can see is some of the traces on it zigzag back and forth in sort of an S-shaped pattern, or maybe looking a bit like a long wiggly snake. And the reason for that is, if you do that to a trace, you're essentially slowing down the propagation speed, the time it takes for the signal to go from one end of the board to another. Now, why is that important? Well, on motherboards and other digital components, we often deal with very short signals. Our signals are often in the gigahertz rate. Well, the period of 1 gigahertz is 1 nanosecond. And when you have bits that are that short or shorter, it's really important that you receive them at the time you expect. If you're just a fraction of a nanosecond too early or too late, you might be reading the wrong bit. So sometimes what you have to do is delay the bits just slightly as they're going from here to there to make sure you're getting them at the time you expect them. And so that's an application for a delay line type approach that's not necessarily unlike these old color TV delay lines. So I guess the moral of the story is electromagnetic delay lines still have some very specialized uses in modern digital electronics. So there you have it. I hope you found this video interesting. If you did, please consider liking and subscribing. It really helps a small channel like this one. If you have questions or comments, please put them below. It's always fun to hear what you have to say and discuss things. And if you have suggestions for future videos, send me an email. Thanks again for watching, and see you next time.